right, good morning, ladies and gentlemen. We're going to start off today by making a simple circuit with some batteries, bulb, and an ammeter. And then we're going to draw the diagram up there, and we're going to measure the electrical potential difference in 4 different places. Okay, so here's our bulb, here's our batteries, and let's go ahead and link this stuff up. Bloop, 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 bloop.
Okay.
This guy's gonna go
Connecting
here.
the bulb to the ammeter because the ammeter has to be in the circuit.
In the flow.
So that's the negative side, and
I could just
bite
touch
onto
it
that
right there.
spring right, yeah.
Okay, bada boom. Okay, so here it is. Should we draw it first? Oh yeah, we gotta fix that right there. Or should we just add in our, or should we just measure
You know what? Well, write this down, boys and girls. We have a current of how much? What do you want to call that?
Ooh. We'll call that, we're in the middle.
We're using the top one.
The top one. They should have done it.
I know.
Anyways,
I know.
okay, we're in the 500 top one, so that's gonna be 250, 260, 275.
275 milliamps. Go ahead and draw your diagram.
Okay, so the first thing we had was our light bulb right here, right?
Yeah,
Okay, and then over here we have our ammeter, like this, right?
And the ammeter is reading I equals 0.275 amperes. 275 milliamps is 0.275 amperes.
Yeah, okay. And then the next thing that we're gonna be doing is measuring the voltage.
We're going to ask you to write this stuff down, boys and girls.
Yeah.
So first, how about doing it across the batteries?
Battery here? Okay, so here and here. Oops, sorry.
Let's call that, you know, if you want, you could bite them on.
Yeah, it's hard for me to hold them on there and.
We wish you were here struggling with this, boys and girls.
Yeah, there you go, look at that.
Well, that's about 2.75 volts. Write that down, boys and girls. 2.75 volts.
Whoa. Okay, easy, tiger. Okay, 2.75.
And then do it across the bulb now.
Bulb.
Across the bulb is about 2.6. Oops, sorry, you can't see that. It's about
Okay.
2.6 volts.
So 0.275, and then bulb we said 2.
It's 2.75 across the batteries. 2.6 across
Okay.
the bulb.
Okay, 2 point. Miss Moore isn't getting her stuff around here. Okay, and where else should we do it?
Let's do it through the ammeter, from one side of the bulb to the batteries through the ammeter.
Okay, so from here, I'm gonna latch onto this one so it's easier for me. And then right there.
Okay, and no, go ahead and bite it.
Go ahead and bite that bad boy. Oh, it's very subtle there.
That's a little less than 0.1 volts. We'll call it 0.6 volts.
0.6 volts there. And then our last place that we will
It's
measure.
across that green wire from the bulb to the batteries.
Yep. So we're gonna go from right here to, and I'm just gonna clamp it on.
And that's about another half a point. Wait a minute, what would that be? You got 1 volt. So what do you say, 0.6?
It kind of looks like 0.6, 0.75. It's hard to read, right? We'll say 0.6 for now.
Now, actually,
Yeah.
if this is 1 volt and that's 1/10 of a volt, that's a 0.05. So this should be a 0.06, and the other one should be a 0.05, I think.
Well, somewhere in there, right? Because that's gonna be a 3.
Let's add these to the diagram.
Yeah, this it's hard to stare at these numbers here. Okay, so let's see. Our numbers aren't going to be 100%
Across the
accurate
battery.
there. Okay, so across the battery, what do we get?
It was 2.6 volts.
Okay.
Across the bulb. I'm sorry. The bulb was 2.6 volts, and the battery was
you're right.
2.7. 2.6 volts.
Oh, you know what you did, Mr. Boykin? You wrote it inside there. Is that
Doesn't matter. Doesn't matter. You're
Okay.
writing bigger. I can see it very well.
2.75, right?
Yeah.
Okay.
And then across the wire from the bulb to the battery,
From the bulb to the battery.
it was about 0.05 5 volts, and then through the ammeter from the bulb to the battery, which one was that? That was about 0.06 volts.
Okay.
Okay, what does that mean?
Okay, so I think it's a little bit weird when I first did my measurement here that if this is 2.75 volts, why isn't this exactly 2.75 volts?
That's right. Well, first of all, let's put signs, because what's the battery doing to the charge?
Oh, well, so it's giving that energy some energy, right?
Yeah, it's increasing the potential energy of the charge, and what's the bulb doing?
It's sucking it away.
It's decreasing. It's changing that electrical energy into heat and light. So we've got 0.15 volts.
Left, right?
So what's happening inside the wire is the wire has some resistance, and there's a potential drop across that wire of 0.05 volts.
So it's really like a minus right
It's
here.
a minus. It's a drop
Okay.
because it takes energy to push the current through that wire.
Okay.
And then over here through the through the ammeter, that's also a drop of 0.6. By the way, 0.06 plus 0.05 is 0.11. That's almost the missing voltage, right?
Yeah, it's almost missing. It's just this many off, and we probably just didn't read it super accurately.
Yeah, because it was bouncing around. So this is an important stuff. Notice that the increase in potential energy caused by the battery is equal to the total decrease throughout the rest of the circuit.
The voltage,
The
right?
ups equal the downs.
The ups equal the downs, right? And this is cool. It makes sense. It reminds me of the conservation of energy, right?
It should remind you of the law of conservation of energy, because it is the conservation of energy.
Okay, so what is next for us? Where's my pencil here? There we go. Right there. Okay. Find the symbol for a potentiometer on page 515. Okay. Come on over here to my office. Here's page 515. Find it. Where is it?
Right there.
Okay,
That's kind of a strange looking thing.
So in yesterday's homework, I asked you guys to put in a resistor into the homework. So resistor, a potentiometer is just another name for a resistor.
Well, here's the
variable
resistor.
resistor?
Here's a symbol for a resistor. Here's a symbol for a capacitor. Different parts of circuits have different symbols, so they don't have to make a picture of that thing right there.
So we are going to be using a variable resistor, right? We don't have something that's fixed. We don't have an ohmic resistor.
Right, and we have one.
Right here.
That is a variable resistor right there.
Okay, let's talk about this thing. Right, is that what we got next up here? Oh, make a circuit with 2 batteries, the bulb, and the potentiometer. Draw the circuit. Okay, so before we do that, let's talk about what we have here. So here's our resistor, and do you see how on here it has, oops, get over here. It has the start of it right here and the end of it right there.
So this is the wiggly part right here.
Yeah, well, let's take a look at when you say these part, you're talking about the coils, right?
Yeah, what you have here is a white insulator that has iron wire wrapped around it. And you can see, I think you can see right there where one end of the wire is there, the other end of the wire is there. And what you have is a slider like the arrow in the diagram that will move to different places.
So at this point, the resistor is this long?
Well,
and this long?
They just, the path that the current follows.
Oh, because it goes in on one thing, it goes
Yeah.
out the other. Okay. So,
let's take this.
take that one out there. And we're going to add it to this spot right here. It's got to be in.
Either one.
The yellow one! Okay, we'll put this one right there. We're going to attach it over there. Okay, and then let's see, make a circuit with 2 batteries, the bulb, and the potentiometer. So no ammeter this time?
Don't need an ammeter.
Get out of there. Thank you, sir. Okay, clamp around there. Okay, so here it is. You guys see how that's all connected
Go
in
ahead
there?
and bite it to the spring.
Okay, and do we light up?
We light up.
We do. We
Now,
indeed do.
Move the potentiometer.
Okay. Should I read this guy? What does moving the slider?
Well, hold on a
Not
second.
yet?
No, first we gotta just show what happens when you move that slider.
Okay. Oh. Can you guys see that? Can they see what I'm doing with the slider?
Yeah, I got them both in.
Eee.
So bright,
Not
dark.
so bright.
That's like a dimmer switch, isn't it?
It is.
It is a dimmer switch.
Okay.
All right,
So
now let's put the ammeter in the circuit here.
okay.
Take the white one off
Oh, yeah.
and replace it with the ammeter.
Get over here, buddy. Get over here. Come on, this clip is hard to open here. There we go. All right. Okay, we're on. All right, so what does it say to do?
All right, so what does moving slider do to the current in the circuit? All right, she moves the slider. Ooh, it reduces the current. Go back in the other direction. All right, so there's the maximum current right there, and then as she moves it, the current goes down. But it doesn't stop. Even though the light bulb goes out, there's still current flowing, even when she's got it all the way at the other end.
And we're good. Okay.
Cool.
Okay, so
So moving the slider changes the current. What causes the current to be more or less in a circuit, boys and girls?
the resistance.
That's right. So
Right.
we have, when you have more current, there must be less total resistance. And when you have less current, there must be more total resistance.
Right? So this is cool. Okay, so next question. What does moving the slider do to the total resistance in the circuit?
All right. Well, it's changing it.
Right? It's changing it, yeah.
So stop right there. Where is the current going? It comes in the green wire, and where does it go after that?
Well, so it's following, it comes in the green wire and it's going out. Oh, we're talking
No.
about conventional?
In this.
Oh, sorry. It goes in the green wire and then it,
Well, let's say it goes in the yellow wire.
okay, yeah. So it goes in the yellow wire and then what it does is it travels through here,
Yep,
right?
travels through that conductor.
And then it travels through the coils.
and it goes down through the slider, and then it has to go through all those coils.
And then it pops back out on this side. Now, what is happening? So
So what happens when you move it to the other end?
they have more distance to travel here.
The current has to travel through more of that wire, and then move the slider up back to where it was.
Now it's really easy.
Now the current doesn't have to go very far
It
at
only has
all.
to travel that little distance right there.
We've got a
from here to
bright
here.
bulb, and we have more current in our ammeter.
Okay.
Interesting.
Very interesting. Okay, so what does moving the slider do to the total resistance of the current? It changes it, which in turn changes our current. What determines the resistance of any conductor?
This is our big idea for today. What's going to change? So obviously there's something here that changes the resistance of a conductor, and it is what?
The length, baby.
It's how long, how much wire that the current has to travel through.
So, where is this? It has to be on there to work. There we go. All right, so more length is more, whoa, trash can almost took me out. So more length gives you more resistance. Think about that.
Yeah.
That makes sense. More cross-section area is less resistance.
So if you got a real skinny wire, it's going to have more resistance, and a big fat wire will have less. What, use that rally
Oh yeah,
analogy.
yeah. So we're at the rally back in the good old days, and we're doing our thing. And Mr. Boykin has just finished up his decibel meter thing that he hates doing. That he loves doing. No.
Yeah.
And they open up two of the
The rally's over. Everybody has to get out, and
And
there's
they
only
open up the
two
doors.
doors.
and they
They
do a
have to
little penguin to get out, right? They're penguining.
Yeah.
Right? And so you've got two doors open, and everyone's like,
That's a lot of resistance to
Yeah.
student flow. Open up two more doors.
Okay, then you get 2 times as many people. We're doing less penguin action
Less
here.
resistance to
Yeah.
the student flow.
Yeah, and now if you open all 8 of the doors, it's
Then-
even easier to flow through, and it gets out even faster.
So more cross-sectional areas, like opening more doors to get the heck out of the gym, excuse me. And there's less resistance to student flow. So
Yes.
it's the same kind of thing in a conductor.
Okay, I think that doing the penguin, I love it, okay? All right, so is this my next slider?
Yep, it is.
Okay, so this is tungsten.
Well, what these are pictures, microscopic pictures of the little wire in here that lights up. The wire lights up, but the other wires going to it don't. Why is that?
So we have to let's look at the structure.
Yeah.
Right? And we can describe this as a double helix in the sense that you have a helix, a twisting in this direction. But then if you zoom in and look at what's going on here and on that level, there's also additional coiling and twisting.
Okay, so this is like inside the light bulb. This is on one side, and current has to flow through this.
Yeah.
So they take this thin wire and twist it once so that you get a long twist of these individual ones like this, and then they take that twisted wire and twist it again.
And they twist it again, almost like it's how the resistor has like that white insulator in the inside, but there's nothing in there.
And
right?
so what does that do to the resistance of the wire when you coil it up like that?
Well, you're increasing the length there, right?
Absolutely.
Right. So if you just twisted it once, well, that's great. But then we twist it more, we have more wire there, more length.
So there's more resistance.
Length, more resistance. Yeah.
And so it's harder for the electrons to get through it. They knock into the atoms. The atoms move around faster and generate heat and light.
Yeah, and basically less current. So
also, they make the filament out of tungsten.
Tungsten. Is that what all filaments are made out of?
Most of them, yeah.
Yep, there it is. Okay. Okay, so how would the type of material affect conductivity?
Yeah, they don't use copper inside the light bulbs. They use tungsten for the filament that glows.
Okay, and why is that? So we have this equation here, resistance equals this Greek symbol called rho, where rho is the resistivity of that material, and then the length of that material and the area of that material.
Let's see. It says 544. Oh, here's a list of Here's a list of resistivities of various metals, aluminum, blah blah blah. Semiconductors. Ooh, semiconductors and insulators.
Ooh.
So here is an insulator, 10 to the 16. Here's a conductor, 10 to the -8. That's a wide range of resistivities that's determined by the material that you've got.
So this is determined by the material, that's length, that's the area, and that gives you the resistance.
So if you know what you got, the length of the wire, the cross-sectional area of the wire, and what it's made out of, you can calculate the resistance.
Okay. So, and then we have a lovely table here. Okay. So we've got different materials: copper, aluminum, graphite, silicone, and quartz. And if you are curious about the units, holler at me in class, and I will kind of walk you through that.
Yeah. We're going to be playing with copper today. That's 1.7 × 10 to the -8 ohm meters.
Okay. And then check out how much different quartz is, right?
Yeah, quartz doesn't conduct electricity at all. It has a high resistivity. Copper is an excellent conductor. It has a low resistivity.
Yeah, and there's your definition there of resistivity, right? It's how much something resists the flow of electrons through it.
That's right. Yep.
Right, and so quartz is really going to resist it. Doesn't want to do it. It's not going to conduct electricity. Copper is like, come on through, right? Okay, so I think we can talk about this here. Okay, so let's go ahead and do an example problem. I'm going to erase you guys. Check it out. What would be the resistance of a 35-meter copper extension cord with a cross-sectional area of that meter squared?
So what is this? 35 meters. That must be the, well, if it tells you the cross-sectional area, that must be the length, yeah? So R is equal to rho L over A.
Okay, so...
and that copper was...
Oh yeah, what was it?
1.7 × 10 to the -8 ohm meters.
Okay. And then what is our length here? 35 meters?
35 meters.
Okay, divided by...
5.2 × 10 to the -7. Grab a calculator here.
Thank you, sir. Okay, so let's do this. So 1.7 times 10 to the negative 8th times 35, and I divide that by 5.2 times 10 to the negative 7th, and I square that like that, and I get this really big number. I think I put that in the calculator.
No, you don't
wrong.
square the area.
Oh, what the heck? Oh,
Don't
sorry.
square the area.
Yeah. But also, what do I have I have a half thing. Oh, no. I thought that was a half. You see that? But it's just the squared.
Okay.
Okay, delete that. There we go. Okay, let me make sure I put that in right. Negative 8, 35 divided by 5. Okay, so 1.14
1.14 ohms.
I was like, that's not right. 1.14 ohms.
So that's about a little more than 1 ohm in a copper extension cord. And do you want to have an extension cord high resistance or low resistance?
Well, you want low resistance, right?
Yeah, because it's going to steal electrical potential energy.
You're trying to get energy that far away. But,
Yeah.
you know, you don't want it to be too
So
far.
you want a fat extension cord. Excuse me.
Okay, here we go. Okay, so we're still talking about copper here.
Yeah.
So it
You know what? They could do this, couldn't they?
Yeah, they could do it. It says a 16 gauge wire has a cross-sectional of copper, has a cross-sectional area of 1.3 times 10 to the negative 6 meters. What squared? What would be the resistance of 75 meters of that cord? Plug it in, do your thing, multiply by your length, divide
Make
by
it
your
happen.
area. You got it. Cool. Okay. Okay. 2 times the radius will give you the distance.
You know what the diameter is, right?
Or diameter, sorry.
2 radii make a diameter. And here's the areas, because we're dealing with circular things. Here's the area of a circle, pi r squared.
Okay.
Just a reminder.
Why am I pi r squared, okay. How could we find the resistivity of the mystery rod?
Mystery rod.
So we're trying to figure this out?
Yeah, we want to find the resistivity.
Okay.
And this, boys and girls, is the mystery rod.
So Wicken, do you mind if I first solve for resistivity here?
I think that's a great idea.
Okay. So if I solve for resistivity, I'm just going to multiply by A and divide by RL. Whatever, you guys get it. Okay?
So what we need to do is find the resistance of the rod.
The area of the rod.
And we need the length of the rod.
Okay. No, I'll leave that there.
And the diameter.
All right, so
we have already done that using vernier calipers.
but we'll show you. My pen is breaking.
Uh-oh.
We're good. Okay, so what should we do first? Do we measure the resistivity?
Well, we've already got the length of the rod. What was the length of the rod?
We said that the length of the rod was. Sorry, I have to find it on my. Oh, here we go. Should we use the first one that we got? The first measurement.
Yeah.
Okay, 0.01945 meters.
So 0.01945. You can go ahead and put it in there if you like.
Okay. This thing is so sharp.
Yes, it is.
It scares me a little bit. There we go. Gotta get it in between. This is hard to use. There we go. So we measured it like this.
Yep.
Okay. And we got it's measured in centimeters, so we had to convert it. So 0.01945 meters.
0.01945 meters. L is equal to 0.01945 meters. Boys and girls, write that down.
All right. And then the next thing that we did was we measured the diameter.
Measure the
here.
diameter.
Okay. And the diameter was 0.00215 meters.
0.00215 meters. So that's the diameter, if that's a diameter, how do you find the area?
We're gonna divide. Well, we
First you need the radius.
We need the radius, so let's divide it by 2 there. Okay, so should we let them just handle that part?
Yeah, you go ahead and,
Okay.
find the area while we find the resistance. How can we find the resistance of this thing?
Okay, well, we gotta plug it up in here. Okay. Now, should I kind of on the end here like this, Boykin? Or should I do it how you had it before?
That'll work.
This will work? Okay, and then we'll take this off.
Yeah, we don't need, yeah, we are gonna need the ammeter.
Oh,
You don't
yeah.
use the ammeter for that.
Oh, okay. Oh, I see.
All right, so what
Wait, are we gonna measure? Oh, yeah, you're right. Sorry, I apologize.
All right, so now we flow the current, and that's about 0.9 amperes.
So
0.9 amperes.
Okay.
And now we need to measure, so go ahead and hook the voltmeter.
Up there.
And then we'll flow current.
Which
And
one's
that's
the
about
thing?
1.35 volts. About 1.35 volts.
Volts. Okay.
So we've got the current, we've got the electrical potential difference. Find the resistance. Boys and girls,
Okay.
you can do this.
So did we said we wanted to help them with it, or should we give it to them for homework?
I think we should give it to them for homework.
We'll go over it tomorrow.
Yeah.
All right. Good luck, you guys.
Enjoy.